Hello, everyone. In this lecture, I'm going to continue our previous discussion that we started on continuous random variables. Uh, I'm going to do this lecture in several parts. Each part will be roughly 30 minutes. Uh, so in this lecture, I'm going to discuss about something called order statistics and also empirical cumulative distribution function, and then relationship between probability density function and probability, moments and shape characteristics of distributions, and tight confidence range. And if time permits, I will discuss some problems also for some activities. So let us start with the order statistics. In our previous lecture, we discussed about the distributions of some functions of random variables. In particular, we talked about linear transformations, linear transformation of a single variable. And also we discussed about linear combination of several variables. How to find out the distributions of that kind of functions of random variables using the moment generative function technique. So order statistics also, actually order statistics, when you say order statistics, there are several order statistics. Right? So suppose you have a random sample x1 up to xn. X1 is a random variable, x2 is a random variable, and so on. Xn is a random variable. Be a random sample from a population or some distribution. Now, when we put these random variables in ascending order, there will be a random variable representing the first or the minimum of the sample of size n. And also at the right end, there will be the maximum of the n random variables. And in between that, there will be, after the minimum, there will be the second smallest random variable, third smallest random variable, and so on. So these all minimum of x1 up to xn is a function of x1 up to xn. Maximum of x1 up to xn is a function of x1 up to xn. And similarly, the second smallest one, third the smallest one, are also functions of x1 up to xn. So these new random variables, the minimum, the second minimum, third minimum, and so on up to the maximum, all are functions of x1 up to xn. So they are actually statistics, right? Statistic is a function of random variables. There is some other words that qualify for this thing. Statistic is a known function of observable random variables. So when you say x1 up to xn here, we are considering some observable random variables, right? And then minimum is a known function, maximum is a known function. So these new functions, minimum of x1 up to xn, second minimum, third minimum, and up to the maximum, they all are statistics. They are called order statistics. Order statistics. So we can actually talk about two types of order statistics, right? For example, even when you're talking about random sample, x1 up to xn, We usually denote random variables by capital English letters x1, x2 up to xn. They all are random variables. They all have some distribution. If the random variables are IID, they all will have the same distribution, identically distributed. If they are independent, then x1, x2 up to xn are independent. Then corresponding to these things, once we observe a particular, when we take a particular sample, for that sample, we have an observation for x1. Usually we denote it by simple x1. The observed value in for x2 is usually denoted by x2 and so on. Observed value of xn is denoted by simple xn. Right? So that simple x1 up to simple xn set of those values is called a realization of the random sample capital X1 up to capital Xn. Or it is simply the observed sample. If you take another set n values, in that case, x1 will be a different number usually. X2 can, simple x2 can be a different number like that. Simple xn will be a different number usually. So there is a set again. Some of them may be the same as the previous x1 or x2 and so on. But generally they can be different. So that is going to be x1 up to xn. That set of numbers is going to be another realization of capital X1 up to capital Xn. So that's the word realization or observed sample. So similarly, when we talk about order statistics, we can talk about two quantities. One is the observed order statistics. The other one is the random order statistics. Right. So suppose we have an observed sample or realization, simple x1 up to simple xn. So these are just numbers. Right. So we can now put them in the increasing or ascending order so that the first number will be the minimum of x1 up to xn, and then the right end you will have the maximum, and in between you will have a second minimum, third minimum, and so on. So out of these x1 up to xn, you will have some value which is the minimum, and that minimum we denote by x subscript within bracket 1. So this x subscript within bracket 1 is going to be one of these numbers. And then we find out the second smallest one, and that is going to be denoted as x subscript within bracket 2, like that. So we are going to have this set of observed values denoted as x subscript within bracket 1, x subscript within bracket 2, and so on up to x subscript within bracket xn. Now here in the realization, x1, x2, xn doesn't have a particular order. x2 can be smaller or larger than x1, x3 can be again smaller or larger than x1 and x2, right? They can be in any order. But here, once you put them in the increasing order, this number is always smaller than or equal to the next number, and so on. Xn will be the largest number. So there will be an order in between these statistics. These are observed statistics. So x1 is a function of these things. x2 is a function of these things. Therefore, they are statistics. But they are observed statistics. So these ordered sample values are called the observed order statistics. So this is one statistic. This is another statistic because this is a function of x1 up to xn. This is another function. So each is a statistic, right? So collectively they are called order statistics. Right? So x within bracket, x subscript within bracket 1 is the smallest observation and second smallest and so on. Right. So they are called observed order statistics. Now, if you take another sample of size n, x1 up to xn, for corresponding to that, again, you will have x1, x2, x3, and so on. So if you do this again and again and again, in each situation, you will have a value for x, the smallest order statistic, the first order statistic, second order statistic, third order statistics, and so on. So the set of all possible values that x1 takes can be considered as the observed values of some random variable, right? Set of all possible values that will be coming as this number based on different random samples can be considered as set of all possible values of some random variable, which we are going to denote as capital X subscript within bracket 1. So therefore, there will be a random variable corresponding to all the x possible x within bracket 1 observed values that we will get if we repeat this experiment. And similarly, there will be another random variable which we are going to denote as capital X subscript within bracket 2. And all the x2 values that would arise if we take different random samples can be considered as possible values of that random variable x, capital X, subscript within bracket 2. So correspondingly, you will have capital X within bracket 1, capital X within bracket 2, capital X within bracket n, random variables. Those are called random order statistics. Random order statistics. So just to show you an example, let us take a random sample of values from some population or some distribution. Suppose these are the values. So you can see that here there is no particular order, but the value that we will denote by x subscript within bracket 1 is going to be 3, because 3 is the minimum value of these. And the next minimum value is 5, next minimum value is 8, the maximum value is 12. Therefore, for this particular set of observations, that is for this particular realization, x within bracket 1 is equal to 3, x within bracket 2 is equal to 5, and so on. X within bracket 5 is equal to 12. So if you take another sample of 5 values from the same population or distribution, then x1 may be some other value, x2 may be some other value, and so on. Right? So as I mentioned, if we repeat this experiment again and again and again, you will understand that there are a set of possible values for the first value here, set of possible values for the second value, and so on. So the set of possible values that is arising from coming as the first or the minimum value can be considered as set of possible values of some random variable. So that random variable is denoted by capital X subscript within bracket 1. Right. So before observing the sample values, the sample observations themselves are random variables x1 up to xn. If these random variables are arranged in ascending order, so what you mean by if these random variables are arranged in the order is what I mentioned a few minutes ago, right? So that's each variable x1 is the random variable of which that we get all the simple x within bracket 1s as possible values. So these are called random order statistics. Now notice that here x1 up to xn are random variables. They have distributions. If they are IID, their distributions will be the same, and they are independent. Especially they are independent. Even if these are coming from the same distribution, right? For example, if all these are coming from uniform, the distributions of x1 up to xn don't need to have the same distribution. They can have different distributions. That is one difference between the original random sample and order statistics. Right? Their distributions can be different, so they are not necessarily identically distributed. Right? Generally, they are not identically distributed. Another important thing is, even if these are independent, these are not independent, because x1 must be less than or equal to x2. right? X1 cannot change freely, right? X2 has to be larger than X1, larger than or equal to X1. X2 cannot take any value freely, right? So there is some restriction. So therefore, these are not independent variables. They are dependent random variables. So here, X1 is the minimum random variable, X2 is the maximum, Xn is the maximum, right? Random variable. Out of these, X1 up to Xn. So they are called random order statistics. They each have some distribution. So for example, X1, X within bracket 1 is actually the minimum of X1 up to Xn, right? It's better actually if I put a curly bracket here to indicate the minimum of that particular set. But sometimes people write down like this also. So minimum of the set of X1 up to Xn is denoted by this. A maximum is denoted like this. And the values in the middle are going to be X within bracket 2 and X within bracket 3 and so. So random order statistics are themselves random variables because their values depend on the particular random sample selected. Although X1 up to Xn are independent and identically distributed random variables, the order statistics are generally neither independent nor identically distributed. Right. So that's something you have to remember about the difference between X1 up to Xn. So just to understand this thing further, let us look at some examples. Right? What do you mean by capital X1? What do you mean by the distribution of capital X1? And so on. What do you mean by Xn, the maximum order statistic? And what can be the distribution of that and so on. So let us consider a situation, just an example. Consider a random sample of size 10 from a uniform distribution between 50 and 100, a uniform distribution. So suppose, for example, X has a uniform distribution between 50 and 100. We are taking a random sample of size 10 from this distribution. So they can discuss about two quantities, that is capital X1, capital X2 up to capital X10, which represents the random variables. So we'll say capital X1 up to capital Xn. X10 here is a random sample from a uniform 50-100 distribution. And so here, for example, X1 represents the set of all possible values that can be as the first observation we get from this uniform distribution. X2, capital X2 represents the set of all possible values that will be the second observed value, right? And then for a particular realization, we can talk about a simple X within bracket 1, simple X within bracket 2, and so on to simple X within bracket 10 here. So what I'm going to look at is, particularly in this case, the following graph. I'm going to draw the graph of the distributions, right? Sampling distributions. In the last class I mentioned, I think, if I remember correctly, whenever you talk about the distribution of some statistic, right? Again, to remind you what a statistic is a known function of observable random variables. Right? So whenever you talk about the distribution of some statistic, usually you call it the sampling distribution. Sampling distribution of sample mean, because sample mean is a statistic. Sampling distribution of sample proportion. Right? Similarly, here we are going to find out sampling distribution of the minimum, sampling distribution of the maximum, sampling distribution of the second order statistic, and sampling distribution of the fifth order statistic, just to get some idea, right? So how do we do this? I'm going to, first of all, what I'm going to do is I'm going to consider several large number of random samples. Each sample is of size 10. right? So I'm going to take one sample of uniform sample of 10 observations from uniform 50, 100, 50 and 100 distribution, and then put them in the increasing order, ascending order, and then find out the minimum value, the second minimum value, the fifth minimum value, and the 10th minimum, right? And then I'm going to take another, I'm going to record those four values first, and then I'm going to take another random sample of size 10 from the same uniform distribution, and then again find out the first order statistic, observed second order statistic, the fifth order observed order statistic, and the 10th one. So I'm going to record them again. So do this again and again and again 10,000 times, a large number of times. Then I will have 10,000 values, possible values for the first order statistic. I'll have 10,000 possible values for the second order statistic. I'll have 10,000 observed values, so possible values for the fifth order statistic, and similarly 10,000 values for the largest or the maximum. Right. So what I'm going to do is I'm going to start with some empty vectors. Say, let's say I'm going to denote them by capital X1, capital X2, or capital X5, capital X10. But these are just labels for my columns. So what I'm going to do is I'm going to write a loop for I in 1 to 10,000. What I'm going to do is I'm going to get some data from a uniform distribution. So random numbers, data, I'm calling data, going to be R-unif, 10 numbers between 50 and 100. So then I'm going to sort or put the data in the ascending order. So in order to do that, I use the function called sort. Sort, there is a function called sort. So when I'm going to name that new set of values after sorting, I'm going to put the name sorted data. Sorted data is equal to sort of this data. And then after sorting, I'm going to find out, take the first value, that is my simple x1. I'm going to take the second value, that is my simple x2. I'm going to take the fifth value, denoted by simple x5, and similarly x10. Right? So now I'm going to put this simple x1 into that capital X1, the empty set. I'm going to combine these things at each step of the loop. So new x1 is the combination or concatenation of previous x1 and this simple x1. New x2, capital X2, is the combination of the previous x2 and the simple x2, and so on. I'm going to build this vectors x1 up to x1, x2, x5, and x10 capital in 10,000 simulations, 10,000 times doing the same thing. So at the end of this loop, I'll have 10,000 values in this vector. I'll have 10,000 values in this vector. So all those values in this vector will be a set of possible values for the minimum value when we take a random sample of size 10 from the uniform 50, 100 distribution. And similarly, X10 will have 10,000 values. Those are going to be 10,000 possible values for the maximum of a sample of size 10 when the sample is coming from a uniform 50, 100 distribution. Now, in order to, I want to just look at their graphs. So that's therefore I'm going to actually draw them in the same window, graph window. So I'm going to therefore divide my graphic window into 2 by 2 subsets or metrics. So for that, I have to use this command par. Par is a command that you use to set several parameters related to the graphic window. In order to have 2 rows and 2 columns in my graphic window, I have to use the command mfrow, that is the parameter, is equal to C2 and 2. This means I want to divide my graphic window into 2 rows and 2 columns, right? So once I do that, then now I'm going to draw the histogram of each of these 10,000 values. So first one, I'm going to draw a hist of capital X1. I want to control, I want to have the same same x-axis just to compare these things. Otherwise, it will be difficult to compare, right? And also, I'm going to have the same breaks or bins in my histograms. That will be easy then to compare. Therefore, I'm going to say my breaks of my histogram, I'm going to set them from 50 to 100 because I know all of these values are going to be somewhere between 50 and 100. Minimum is 50 and maximum is 100. Going by 5, I'm going to say 50, 55, 60, 65, and so on. Those are the breaks. And the limits, I'm going to set to 50 to 100, right? X limit of X axis, right? So similarly, and then I'm going to also use some other things, X lab, right? Label of X, I want to write it as X subscript 1. So in order to get the subscript as in the label of the x-axis, I'm using this method called expression. And similarly, I want to put the main title. I want to have a histogram of x1. So this is the command that I use. Right. So similarly, for all the others also, I'm going to draw histogram of x2, x5, and x10. And this is what I get, right? So you can see this is all these have the same x-axis. All these have the same size of bins, right? Bin size, bin width is equal to 5, right? But you can see definitely the original distribution was a uniform distribution. I'm taking my observations always from a uniform 50-100 distribution. But you can see the distribution of sampling distribution of x1 is quite different from sampling distribution of x2. It's quite different from sampling distribution of x5. This is completely different from sampling distribution of x10, right? So that shows you that even though x1 up to xn are coming from the same distribution, the order statistics don't have the same distribution, right? Now, this is what I get. For example, if I want to get a x subscript something as label, you have to use the command expression. X lab is equal to expression, and then x square bracket 1 will give you this. So if you look at this code, you will understand that, right? I will give this a note as usual to you. After this thing, I will post the note. Right? So I want you to clearly understand what you mean by these order statistics. So order statistics they are statistics. They are not independent. Their distributions are not the same. Say for x1 up to x10 are not identically distributed. Now, I would like you to think in this case, why we have this shape for x1, that is the minimum order statistic. Why do we have this shape for the maximum order statistic distribution of the sampling distribution of the maximum? Why do we have this shape and why do we have this shape and so on for these particular order statistics when we are taking a random sample of size 10 from the uniform distribution? Right. So I will stop this session here, leaving for you to think. And then in the next session, we will again start with this one, discussing why we are having these shapes. But before that, I would like you to think about it and have some answer ready. And then we can discuss about that. You can listen to my explanation and see whether your explanation is very similar to that or different. Right. Okay. Okay, welcome back to session 2 of this lecture. At the end of the first session 1, we were talking about the sampling distributions of the order statistics when the samples are coming from a uniform 50-100, 50 to 100 distribution. Sample size is 10. So we were particularly looking at the minimum order statistics, maximum order statistic, second minimum order statistic, and the fifth minimum order statistic, or first order statistic, second order statistic, fifth order statistic, and 10th order statistic. And I invited you to think why we are having this kind of different distributions when the data are coming from the same distribution. In other words, my x1 without any bracket, just x1 has a uniform 100 distribution. X2 has the same distribution. X3 has the same distribution. But this X within bracket 1, that is the first order statistic, has this particular shape here. And the maximum has this last shape and so on. Why are they different? I hope you have come up with the explanation. But anyway, to understand this, let us look at some samples of size 10 from uniform distribution. You see that whenever you take a random sample from a uniform distribution, uh, because the density function is a flat function, the probability that any particular observation will be in a given interval is the same is for any other interval with the same width. So therefore, we expect our random sample to be distributed roughly uniformly between 50 and 100. That means roughly the distance between these observations will be roughly the same, right? They don't have to be equal. Sometimes they can be quite different also very rarely, but more generally, the distances will be roughly the same because they are uniformly distributed. But when you put this, once you have taken a random sample of 10 values and put them in the ascending order, the minimum value will be always close to 50. Right? The minimum value will be close to 50. That means the minimum value is most likely to be close to 50. And the second value, of course, has to be larger than the minimum value, but that will be little larger than the minimum value, right? Uh, but the first one is always going to be very close to 50, or not always, but most likely to be close to 50, right? Very rarely, the minimum value will be close to 100 or even 90 or even 80, right? There's a small probability that the minimum of our sample will be close to 75 or so, but very, very rarely. Right? Only very rarely the minimum of our sample will be more than 60. Right? So just to see this, let us generate some random numbers from uniform 50, 100 distribution and then put them in the increasing order and let us look at the first number, first value. Right. So I have this command here, sort runif 10, 50, 100. So that this part will give you 10 random numbers from uniform 50, 100 distribution. Sort will sort the data. Right. So if I run this, I see you see that these are the numbers that I got. The minimum value after sorting is 50. Minimum value is 50, 50.16. Right, just above 50. If I do this again, right, in that case, see, okay, it was not very close to 50. In this case, the minimum was 62.8. So that was one. But in the next one, let's see, again, it's close to 50 again, 53. Right. If I do it again, now in this case, 54.2. Now 61, right? So you can see that most of the times the minimum will be close to 50, but rarely that will be somewhere around 60, but not more than that. We have done it now several times. We didn't get any 70s, right? It's 54 is the minimum. 55.5 is the minimum, right? 51.2 is the minimum, right? 51.00 is the minimum, right? 50.20 is the minimum, right? 51.68 is the minimum, right? So we got few values which are few minimum values which are close to 60, but not more than 65, right? So if I do this 10,000 times, you will see that most of the minimum values will be close to 50, rarely little larger than that, even more rarely little larger than that, and very, very, very rarely only values somewhere close to 70. After that, a minimum value will not be taking more than that value. The probability that the minimum value is greater than 70 or so will be almost zero. So that's why we have this histogram for the sampling distribution of the uh, first moment, first order statistic. Right? Very rarely only now values greater than 1, right? Uh, the most possible value is between 50 and 55, right? 55 to 60, even half of this, right? Probability of that the minimum order statistic is between 55 and 60 is less than half of the probability of the minimum order statistic is between 50 and 55, right? Actually, this axis shows you the frequency, but if you divide these frequencies by 10,000, you will get the probability in this case, right? Now let us look at the maximum in the same idea, right? So when you take a random sample of uniform, the maximum value is going to be most likely value is going to be close to 100, right? Most values are going to be close 100, very rarely little less than that, even very rarely less than that. So again, if I look at my data, for example, in this, the maximum was 97, here maximum was 98 point, this maximum was 99.3, now my maximum was 95.64, 90.6, right, 94. So you can see that most of the values are between 90, 95 and 100, a little less frequency. uh, the values will be between 90 to 95, right? Very rarely numbers less than 90, right? So that's why we have this shape for the sampling distribution of the maximum of the sample. That is the 10th order statistic, right? Now, in the same idea, you can again understand X2. X2 is going to be somewhat not the most possible values are not going to be between 50 to 55. Most possible value will be somewhere between little larger than that. So like 55 to 60, for example. Right? Uh, so the values for the second order statistic being in this interval will be less than the likelihood of the second order statistic being in this interval here, right? So like that, after that, the likelihood is, or the probability or the frequency is coming down, right? So very rarely the second moment statistic will be greater than 85 or so, right? Here, X5 is actually somewhere in the middle of the 10 order statistics, right? So this X5 is most likely to be the value in between 50 and 100 in the middle. So that means roughly between 70 to 75 or so. Oh, right. So that you can see actually from this one, the most likely value for the fifth order statistic is between 70 to 75, 50. So smaller values are less likely and higher values are also less likely, making the distribution look like roughly symmetric and also kind of bell shape. But of course, this is, as I have mentioned, or not all the bell shape distributions are normal distributions. And actually, in this case also, we can show that this is not exactly a normal type of distribution. I'll talk about the distribution a little later, but it is somewhat bell shape and somewhat symmetric. And then this one we have already talked about. Right? So that's why we are having these different shapes for the sampling distributions of different order statistics, even though the original data are coming from the same distribution. So here I'm just showing you the pictures. Later on, maybe in in the third chapter, we will be deriving the mathematical equations for these sampling distributions, and there we will actually see that all these are some kind of beta distributions. Beta distribution is again a family of distributions. I didn't discuss this thing in my previous sections, uh, where I have discussed about some models, but I didn't discuss about the beta distribution. But when the time comes, I will again discuss about the beta distribution. Beta distribution is actually a good model when the data are in a restricted interval. For example, in this case, uh, my data are original data are in between 50 to 100, 50 to 100. So all these x1 up to x5 are also going to be somewhere between 50 to 100. They cannot be less than 50 or greater than 50. So it's a restricted area, but the distributions are not uniform now. So this is another possible model when the data in a restricted area is actually a beta distribution. So but they are not the same beta, like uniform or the original data were coming from the same uniform distribution. Uniform distribution is also a model suitable when the data are in a restricted area, say restricted range, domain, right? Like 50 to 100. But that has a flat density function, right? So this is one beta distribution. This is another beta distribution. This is another beta distribution. This is another beta distribution. But all of them are going to be some beta distributions. Later on, we will find out the actual mathematical formula for those distributions. Right. Okay, let's do the same thing again. But now, in the previous situation, I generated the data from a uniform distribution, where the distribution, original distribution, was also symmetric, right? Because it's a rectangle distribution. It's a symmetric distribution around 75. But now let me consider the parent distribution being exponential, very skewed, positively skewed. Suppose you are taking a random sample of size 10 from an exponential zero point 0.01 distribution. So in this case, lambda is equal to 0.01. The mean is equal to 1 over lambda, that is equal to 100. Right? So let us again look at the sampling distributions of the minimum, maximum, and the second order statistic and the fifth order statistic. Now I'm not going to discuss why we are having this kind of shapes. So I invite you to do the same thing using your R, and then think why you are having this kind of shapes for the sampling distribution of the first order statistic, second order statistic, fifth order statistic, and the 10th order statistic. Right. Notice if you remember the original distribution, the uniform distribution, what is the shape of that? Uh, the shape of the original distribution is a very positively skewed distribution. Right? So that actually has roughly the same shape of the first order statistic. So I'm sure you remember the shape of a exponential distribution, right? So exponential distribution, uh, the density function is something is wrong here. I don't know why it is just it doesn't okay. Fx is equal to something is wrong in my writing pad. Uh, lambda e to the power minus lambda x, where this lambda has to be a number greater than 0 is the parameter. It's called the uh, scale rate parameter, and then x has to be greater than or equal to 0. So here when x is equal to 0, you see that fx is equal to lambda. So in this case, somewhere here, say for example, and then the density is coming down like this. So that is the original distribution. So my x1, x2, all are coming from this distribution up to x10. Something is wrong. I don't know what it, but okay, that is enough. Right. So when all the data are coming from this particular distribution, uh, you can again see that the order statistics have different shapes. Right. We will again derive the mathematical equations for these distributions. You will see that they all again coming from the same family, but with different parameters. Right. Okay. So now you know what we mean by order statistics, right? And what we mean by the sampling distributions of order statistics. Now let us look at one or two practical examples where we can use these order statistics. Uh, this example, the lifetime of a certain type of bulbs is normally distributed with mean 1,000 hours and standard deviation 100 hours. Right? So some kind of bulbs, each bulb has a certain lifetime, and somehow using some modeling uh, experience, they have found out that a normal distribution with mean 1,000 and standard deviation 100 is a suitable model for the lifetime data for this particular bulbs. Okay, you have bought 10 of these bulbs. Suppose you have bought 10 of these bulbs. What is the probability P1 that each bulb will work at least 900 hours? And the second question, what is the probability P2 that each bulb will burn out before 1300 hours? Answer using theory as well as using simulation. Right? We can answer these two questions using theory and simulation. Actually, in theory, we can apply two methods here. I'm going to discuss here only one of those methods. The second method will be discussed later when we actually find out the sampling distributions of order statistics, formulas for those. But here I'm going to use something that we already know, right? So let's look at the first one. What is the probability P1 that each bulb will work at least 900 hours? Each bulb has the lifetime which is distributed according to a normal distribution with mean 1,000 and 100 standard deviation 100. Right now we are looking at 10 bulbs. So we need to find out the probability that all 10 bulbs each will have more than 900 hours. Right. How can we answer this question? We can answer this question using this model, given model, normal distribution, and also binomial model. Right? We can find out the probability that any of these 10 bulbs, what is the probability that any of these 10 bulbs work at least 900 hours. Right? So if I say, for example, the lifetime of the first bulb is x1, I can find out the probability that x1 is greater than or equal to 900. And similarly, I can find out the probability x2. Suppose x2 is the lifetime of the second bulb. So what is the probability? X2 is greater than or equal to 900 and so on. We can find out, and they will each will have the same probability because x1, x2 up to x10 all have the same normal distribution. Right? So we can easily find out this probability using R. That will give you 1 minus the probability that what you need is the probability that any x, let's say x1 greater than or equal to 900, that is equal to 1 minus the probability x less than or equal to 900. So you can find out that using 1 minus p norm function, 1 minus p norm 900, 1000, 100. That will give you the probability that any bulb is lifetime is greater than 900. Now what you really need is P1. P1 is the probability that all bulbs each have more than 900 lifetime, right? So actually the number of bulbs which have more than 900 lifetime will be will have a a binomial distribution. If you say n is the number of bulbs out of these 10 bulbs which have lifetime more than 900 hours, then n will have a binomial distribution with 10 and some probability of a success, where the probability of success is the previous probability that we talked about. So using that, we can find out the probability. In simply here, because each bulb, all the 10 bulbs have to be having more than 900 hours of lifetime. The probability of that will be the probability that any bulb will have more than 900 hours of lifetime to the power 10. That's again coming from a binomial distribution, right? And similarly, here we will answer the second question. And we can do the same problems, answer the same problems using simulations also. So let me look at the first answer. Here, just to give you some idea about the sampling distributions, here I think you have already understood that actually we are going to look at what is the probability that probability P1 that each bulb will work at least 900 hours. So each bulb will have lifetime more than 900 hours if and only if the minimum of this lifetime is greater than or equal to 900 hours. Right. So therefore, we can answer the same question, that is the second method, by finding the probability that the minimum order statistic being greater than 900. Right. The probability that x within bracket 1 greater than or equal to 900 will be the same as the probability that each of these bulbs is lifetime is greater than or equal to 900. And similarly, the second one, what is the probability P2 that each bulb will burn out before 1300 hours? Each bulb will burn out before 1300 hours if and only if the maximum of lifetimes of these 10 bulbs is less than or equal to 1300, right? You can understand this if and only if thing, right? That means it goes both ways. If the maximum lifetime is less than 1300, all or each lifetime will be less than or equal to 1300 hours. And the other way around, if each lifetime is less than or equal to 1300 hours, the maximum will be less than or equal to 1300 hours. So therefore, we can answer that question using the X10, 10th order statistic. So therefore, in order to get some idea about the sampling distribution in this particular case of X1 and X10, I have, using the same previous method, I have generated 10,000 values, 10,000, taken 10,000 samples of size 10, and from each I have found out X1 and X10, and thereby drawn the sampling distributions of X1 and X10 when the data are coming from a normal with mean 1000 and standard deviation 100. Right. So you can see that again the distributions are different. In this distribution is somewhat left skewed. This one is somewhat right skewed. Right. So we can find out what is the probability that the minimum is greater than this question. First question, what is the probability that the minimum is greater than 900? So from this histogram, I can estimate that probability. 900 is here. I have here, this histogram is coming from 10,000 values. So what is the frequency that the minimum value is greater than 900? So this is roughly 1,500 and again roughly like 200. But I can actually get the number of values, exact number of values from my simulation. So that number divided by 10,000 will be the estimated probability that all the bulbs will have at least 900 hours of lifetime. And similarly, the second question, using order statistic, I can find out looking at the maximum order statistic. What I need is the probability that the x10 is less than 1300. So here from this histogram, I'm looking at this total frequency here below that divided by 10,000. Right? Here total frequency above 900 divided by 10,000. That will be my estimates from the simulations, because I have got these things from simulations. So I can get the answers to the second two questions using simulations like that. But using theory, how do we do that? Using theory, what we do is this. Okay, let's do that. The first one. So first I'll find out the probability that any bulb will have lifetime less than 900. Greater than 900. So that will be equal to 1 minus P norm 900, and then mean is 1000 and standard deviation is 100. So I will give a label for this thing. I'll say A, for example. This is the probability that any bulb will have lifetime greater than 900. Right. So P1 will be then A to the power 10. Right. All the bulbs, each bulb, the probability that each bulb has lifetime more than 900 hours. Right. So A to the power 10. So what is the value? Value A is 0.84. Right. And P1, this is the theoretical value. Okay, I didn't run this one. Okay, I run this one first. And then P1 is equal to 0.171. So that is the theoretical probability that all the bulbs will have at least 900 hours of lifetime. To answer the second question, I need, first of all, to find out the probability that any bulb, any single bulb will have lifetime less than or equal to 1300. So I'll call it that B. So that is less than or equal to, I can get it directly from P norm 1300, and then 1000, and then 100. So that probability B, let's see what that value is. That is 0.99865. That is the probability that any single bulb will have lifetime less than or equal to 1300. So what I need is now probability that all the bulbs will be having less than that amount, 1300 hours of lifetime. So my answer will be then B to the power 10. B to the power 10. Right. So B to the power 10 will be 0.986583. Right. So this is my theoretical value for the first answer. This is my theoretical value for the second answer, second question. This is my simulation value that I got from this histogram, right, or 10,000 values. So I look at the number of values that I got for x1, right? I use the same commands that I used earlier to generate these ones. So I have values in x1. So now I find out how many values are greater than 900, right? Greater than or equal to 900. So what for that, what command can I give? Suppose, for example, I have all my first order statistics values in capital X1. So now I want the number of x1s greater than or equal to 900. So this is the condition, right? So this condition, if I give this condition, there will be some out of these 10,000 values, some of values will be trues, some of them will be falses, right? If any x1 value is greater than or equal to 900, there will be a true word, true. otherwise false. So how many truths you can get by just adding these things? Sum, right? Sum x1 greater than or equal to 900 will give you this value here. That's the value that I got. So you can see that actually the theoretical value is 1.177. The simulation value that I got in this particular simulation was 0.1739. If I do another simulation again, starting from scratch, I do it 10,000 times, I will get something like 0.1741 or something. It doesn't have to be the same value, but it will be again very close to this 0.17 value, right? You can see that answer is uh, very similar up to 2 decimal places. And for the second question, again, you can see the theoretical value and the simulation value are quite close. Theoretical value is 0.98. Simulation value is also 0.98. So answer is close up to 2 decimal places. Right. So I think that is why I forgot to set up my timer. I think I have already taken about 30 minutes. Therefore, I'll stop my explanation here and look at another example in the next session. I will look at this example in the next session. So I will just put it here. A product consists of 4 similar components connected in series. The product stops functioning when any of the components fails. Assume that the lifetime of the components are independent and exponentially distributed with mean 1000 hours. Let x1 up to x4 denote the lifetime of the 4 components. The questions are: find the mean lifetime of the product, find the probability that the lifetime is greater than 500 hours, find the value below which 95% of the lifetimes lie. We can answer this question also theoretically as well as simulations, but I am going to only apply the simulations at this moment. I will leave the other part, theoretical part, for you to do in the class, do by yourself, right? So I will discuss this in the next session. Right? So the problem is here. Okay, this is the part 3. Let us continue with the example that I mentioned at the end of the last part. A product consists of 4 similar components connected in series. The product stops functioning when any of the components fails. Assume that the lifetimes of components are independent and exponentially distributed with mean 1000 hours. Let x1 up to x4 denote the lifetimes of the 4 components. Find the mean lifetime of the product. Find the probability that the lifetime of a product is greater than 500 hours. And then there's another part. Find the value below which 95% of the lifetimes of the products lie. That means find the value below which the lifetimes of the products will be less than. Right. So how do we answer this question? We are going to answer this question now. There are again 2 methods that we can do. One thing is, first of all, we'll have to identify the random variable that represents the lifetime of the product. What we know is about the lifetime of each component. Right? There are several 4 components connected in a series. Each component has a lifetime which is exponentially distributed with mean 1000 hours. That means rate parameter will be 1 over 1000. Right? Rate parameter lambda is 1 over 1000. So they are IID, independent and identically distributed x1, x2, x3, x4. So In terms of x1, x2, x3, x4, what will be the lifetime of a product? The product stops functioning when any of these components fails. Right? So that means the product will stop functioning when the first component fails. I mean, not the first component, actually the one of the components fails, right? The At the moment, the one of the components fail for the first time, the product will stop. Right? So therefore, we can see that the lifetime of the product is actually represented by the first order statistic, the minimum of x1 up to x4. The lifetime of the product is represented by the minimum of x1 up to x4, that is the first order statistic. Therefore, our variable of interest in this case is the first order statistic, which is denoted by x subscript within bracket 1. So when the question says find the mean lifetime of the product, what you have to do is find the mean of the first order statistic. Find the probability that the lifetime of a product is greater than 500. That means we have to find out the probability that the first order statistic is greater than 500. Find the value below which 95% of the lifetimes of the products lie. There we have to find out the value of the first order statistic, so that the probability that the first order statistic less than or equal to that value will be 0.95. Right. So these are the three questions that we have to answer. Right. First, identify the variable of interest in terms of x1 up to x4. We know that each x1, x4 has the same exponential distribution. Right. One thing we can do is we can theoretically derive the distribution of the first order statistic, and then in the usual way we can find out the expected value, we can find out the probability, and we can find out the quantile using the theoretical distribution of the first order statistic. That is mathematically a little bit intensive, right? Much easier way is to get an approximate value, not the exact values, but very much close and approximate values using simulations. So what I will do is we will simulate about 10,000 possible values of x1, assuming that x1 up to x4 are exponentially distributed with rate parameter 0.001, 1 out of 1,000. Right? And then using those 10,000 possible values of x1, we can answer these questions. We can get approximate answers. Right. So let us together write down an R program. So as I mentioned, what I'm going to do is I'm going to generate 10,000. If you want, if you can generate more than that, but 10,000 values will be reasonably a large enough number of values to get the answers quite accurately, right? So what I'm going to look at is the minimum, right? Or the first order statistic, usually denoted by x subscript within bracket 1, but here I just denote it by x1. So I'll first create x1. I'll create an empty vector because I want to build up that vector by generating a sample of size 4 observations from an exponential distribution with rate parameter 0.001, and then finding the first order statistic value, and then combining that with capital X1 and do that 10,000 times to generate 10,000 possible values of X1, right? So here I start a loop for I in 1 to 10,000. What I'm going to do is first generate data. Data is going to be REXP, random numbers from the exponential distribution. How many? 4 numbers I need with the rate equal to 0.001. Mean equal to 1000 means lambda equal to 1 out of 1000, that is 0.001. So you will have first 4 numbers, then take the minimum of those numbers, right? Or you can first sort them and take the first value, or just directly ask for the minimum value. So let's say I'm using simple x1 as the minimum of these 4 values, and then put that simple x1, combine that one with the capital X1. So at the end of the first one, I will have 1 number here. At the end of the second round, I will have 2 numbers here, and so on. I will generate 10,000 possible values for the first order statistic when the data are coming, for observations are coming from exponential 0.001 distribution, right? So to get some idea, I'd like to draw the histogram also. Therefore, I will give this command hist of this capital X1. I will put the label of x-axis. I want to put x within bracket 1 as a subscript. So this is the way expression x within bracket, within square bracket, and then whatever you want in the subscript. I want in the subscript within bracket 1. Right. And then I will also put the main title. Main is the argument that. So that again I want, because there also I want X subscript 1. I'll say this is the way to get it. Expression, then within quotes, histogram of, and then some space. This thing stands for space. And then what I want to get mathematically, X 1. Right. It's better probably. Yeah, here I'm using x simple x1 because I'm just getting the values of simple x1 values, histogram of simple x1 values, right, which is going to be approximately the sampling distribution of capital X1 value, right? So that when I do that, so let's do this, run this thing. So this is what I get. I get histogram of x1 and axis here x-axis x1. So this, you can see that it also has very similar to exponential distribution, but I don't know whether it's exactly exponential distribution. Later on, we will learn how to derive the mathematical expression for this distribution, but it looks like an exponential distribution here. Right. Now, in order to answer these questions, right, I have now, this is actually the histogram of 10,000 values. I have already 10,000 values. To answer the first question, I want find the mean lifetime of the product. So that means I want actually the expected value of the first order statistic. That's what I want really, expected value. But I cannot find out the expected value exactly unless I find out the exact distribution of the first order statistic and then integrate x times that density function and get the expected value. That's a mathematical work. But instead of that, I can get an estimate of the expected value. That is going to be the sample mean of these 10,000 x1 values. So let's calculate the mean of x1. And I'm going to, because it usually gives you numbers, decimal numbers, several decimal numbers. I'm going to round my answer to 1 decimal number. If you want, round it to 2 or 3, whatever. So I'll call it x bar. X bar is the rounded value of mean of capital X1, where capital X1 contains 10,000 values, right? So x bar gives you that. And if I get the value, you will see that mean lifetime is 250, right? Even though individual products have mean lifetime 1000 hours, when this product of 4 components is connected serially, average lifetime of the product becomes only 250 hours. That is because that is the distribution, and that is the lifetime expected value of the smallest order statistic. Right. So anyway, that is the answer that we get. And now the second question asks, find the probability that the lifetime of the product is greater than 500. Probability. So how do I find out that? First, I want to find out of this 10,000 X1 values, how many X1 values, right? I have this 10,000 X1 values. Out of these X1 values, how many are greater than 500? And that number has to be divided by 10,000 to get the probability, right? So let's do that. So I call it P. P is equal to, so this one, X1 greater than 500 will give you the vector of true false when any X1 value is greater than 500, there will be a true, otherwise there will be a false. So if I take the sum of those, I will get how many truths. That means how many X1 values which are greater than 500. Divide that by 10,000 will give you the proportion of those values. And I'm going to round that proportion to 2 decimal places. That's what I'm going to call P. This P will be an estimate for the actual probability that we want, right? So here I want the probability that the lifetime of a product is greater than 500. If you really want to find out the actual probability here, what you have to do is you have to get the theoretical distribution of X1 and then find out the probability that X1 greater than 500. So that means I have to integrate my density function of X1 from 500 to infinity. That's a mathematical work, may not be that easy also. But here, this one is going to give you only an estimate. This estimate will be a pretty good one because this estimate is coming from 10,000 values. So let's calculate that. So my P will be 0.14, right? So only roughly 14% of the products will have lifetime more than 500 hours, right? Average lifetime will be 250.3 hours, right? Only 14% of the products will have lifetime more than 500 hours, right? So the next question, what is the value below which 95% of the lifetimes of these products will lie? So again, if I want to find out this value, theoretically, what I have to do is I have to integrate my density function of x1 from 0 to some value k, and then equate that integration to 0.95, and then solve that equation to find out k, right? So k will be some quantile, 95th quantile of the x1 random variable, the smallest order statistic, 95th percentile of the smallest or the first order statistic. So that's what you have to do if you want to do it theoretically. But you can get the answer approximately very well, very good estimate by just finding the 95th quantile of these 10,000 values of x1 we have, right? We have 10,000 values. So let me find out the 95th quantile of these x1 values and then round that quantile to 2 decimal places, because otherwise it could give me a large number of decimal places. So Q95, I'll call it label. Q95 is equal to, first find the quantile of x1, 95th quantile, and then round it to 2 decimal places. So let's find out what this value is. 754.2. So that means 95% of these products' lifetimes will be less than or equal to 754 hours. 754 hours. Right. So that's how we can use these ideas of order statistics to get this kind of answer this kind of question. So you can see that's very useful, right? Very useful. Right. Otherwise, the mathematical calculations will be quite different sometimes, but this is a much easier way to do it. So here, after I have got my values, for example, the mean and the quantile, I have added those two to my picture graph right here. Right, so I can do that. If I want to add some vertical line at a point, what I do is after my graph histogram, so I have this histogram. Now I say AB line. AB line usually draws any line with a given uh, intercept A and slope B. But here what I want is a vertical line. So in that case, I say AB line V equal to 500 because I was looking at uh, the probability that the lifetime is greater than 500. So that is 500 is here. And the probability that the lifetime is greater than 500 will be given by the area under the curve divided by 10,000 here because this frequency. You have to get the area. Area will be given as a frequency, but then you have to divide by 10,000 to get the probability. Right. But here I'm just showing you how to get some vertical lines if you want. Right. So when you say AB line V equal to 500, if you want, you can specify the color also. Here, color equal to 2 means red color, or you can say color equal to red here. Both will give you the same thing, red color line, right? You can see that. And then I'm also drawing a vertical line at this point, Q95 value, right? That color is like green. This is color equal to 3 means green, right? So that means this is the 95th quantile, right? The probability or the area under this below this will be 95% of the total area, right? Okay, so that's one example. So this is what I got when I ran it, because now these are simulations. These values are coming from 10,000 simulations, so therefore the answers can be slightly different time to time. For example, in the previous case, in the when I did it here, I got 250.3 as the mean. When I did it earlier, it was like 249.6, which is again 250 approximately. And this probability I got now, I got 0.14, but earlier I got 0.13, right? The quantile, now I got uh, uh, 754. Earlier, I got 753, right? So they can be slightly different because they are coming from randomly selected numbers, right? So if different people are doing these simulations, they might get different answers, but very, very close to each other, right? So let's look at one final example for the order statistic application. Uh, A communication system consists of 5 servers operating independently. 5 servers. The lifetime of each server is exponentially distributed with mean 200 hours. The system can continue functioning as long as at least 3 servers are operational. At least 3 servers are operational. In the previous section, previous problem, we needed all uh, of them to work, for the system to work. But here there are 5 servers. If at least 3 of them are working, the system will still work. Identify the random variable representing the lifetime of the communication system, right? So suppose the lifetime of these 5 servers are x1, x2 up to x5 capital, right? Now in terms of x1 up to x5, what will be the lifetime of the system now? You have to identify that. Find the probability that the communication system operates more than 100 hours. So similar to the previous problem, once you have identified the random variable, you can generate that random variable, the distribution, and then from that you can estimate this probability. And similarly, find the probability that the communication system fails within the first 150 hours, you can do the same thing similar to the last question of the previous problem, right? So I'm going to leave that as an activity for you because it's very similar. Only problem now is to identify the variable of interest representing the lifetime of the communication system. And then after that, all the operations will be quite similar to the previous problem. Right. See, I'm asking you to find out the answers using theory and also using simulation. It might be difficult for you to find out the answers using theory at this moment. So just leave it for us to do later. Do is using the simulation. Right. So that's the end of that section called order statistics. The next topic that I'm going to talk about is something called empirical cumulative distribution function. Right. You already know what the cumulative distribution function is, right? Cumulative distribution function is for a random variable x, right? If you have a random variable x, the cumulative distribution function is denoted by capital F subscript capital X and then evaluated at some real number simple x. By definition, this is equal to the probability that capital X, that is the random variable, less than or equal to simple x, right? So that is the theoretical cumulative distribution function, CDF. Right? This is correct regardless of the type of the random variable, whether it is discrete or continuous, the same definition, right? Now we are actually, this is a theoretical quantity actually. So for example, if suppose you assume that a random variable x has some exponential distribution, right? When you say exponential distribution, it comes with the unknown parameter, lambda, rate parameter, right? So theoretically, you don't know the actual distribution. You might even, you might select a model that is a member of a certain family of distributions. So exponential distribution with some unknown rate parameter lambda, for example, or you might think that capital X has a normal distribution with some unknown mean mu and unknown variance sigma square. So when you forget the cumulative distribution function, it also contains those parameters. Therefore, theoretically, these are we know the form of the function, but we don't know the function completely because there are some unknown quantities inside those functions. So therefore, practically, these are unknown functions. Cumulative distribution function, density functions are unknown functions. What we practically do is we use some data to estimate those unknown parameters and then use those estimated parameters as actual values. And then the density function or the cumulative distribution function with those values regarded as actual values are used to answer the questions. That's what we usually do. Right? So that is the parametric method of answering a question. Parametric method. That means you assume some model for your the density function or the distribution function of your random variable. And then using the data, you estimate the parameters of interest and then consider those estimated values as the actual values and thereby consider the assumed model with those parameters as the actual model, actual distribution, and use those distributions to answer the questions, to calculate the probabilities, to calculate the models, and so on. So that is the parametric method of answering questions or doing inferences. There's another way without assuming a particular model, without assuming an exponential distribution or without assuming a normal distribution. We can answer the similar questions like calculating the probability, actually not calculating, estimating again, but without assuming a particular parametric model. That method is called non-parametric method. In the non-parametric method, we can get an estimate for the cumulative distribution function, and we use that estimated cumulative distribution function without assuming a particular model. And then we use that estimated cumulative distribution function to answer our questions, like calculate or estimate probabilities, estimate quantiles, and so on. So that estimated cumulative distribution function using a data set of X is called the empirical cumulative distribution function. Empirical means using the data. Right. So that is what we are going to look at next. We are going to look at how to get the empirical cumulative distribution function and what are the properties of that empirical cumulative distribution function and what we can do with that and so on. We will discuss those things in the next section. So for the moment, I will stop this session now.